Hello everyone, welcome back to GenAI Crash Course. So far we have covered OpenAI, LangChain, but as we observed in the very first video of this course, LLMs don't have any idea about data that is beyond their training data. So this is where vector database come into the picture. In this video, we are going to explore vector databases in detail. We'll explore what they are, how they work, why they are essential for AI applications nowadays, and you'll also learn how to store embeddings, perform similarity searches, and integrate a vector database into AI workflow. So without any delay, let's get started. Okay, so we are back in VS Code. Let's create a new cell and make sure that everything is working. Okay, it's working. For this particular tutorial, I don't think we need the .env yet. We need it in a bit of time. Okay, let's understand what exactly are vector databases. In one of my previous video, I've explained what exactly are vectors, what are embeddings, why do we store them, how do we store them, how do we retrieve them, all of that in detail. But I didn't explain how can we build a vector database and how can we build it especially for AI applications. So today, that is exactly what we're going to do. We're going to take data about certain company and we'll create a vector database completely dedicated for that company. For this particular demo, I've chosen. Okay, if I go to this particular website, Larsen and Tubro, so this is the L&T official website from which we are going to take all of this data and then create a vector database. If I go to awards and recognition, you can see they have a lot of different awards and we have data about all of that part. And if I go into corporate policies, we have all these different policies. If I go into climate strategy about sustainability, we have all of this data about that part. So we've got all these different web pages. Now from these web pages, I'll extract the text and then I'm going to create a vector database out of it. So usually when we are working in general, if you want to find out answer for a certain question, you can just think, and from whatever parts of your brain, wherever you have stored that particular information related to that topic, you'll be able to remember that part. Similarly, in the vector database, we are going to take all this data, we'll convert them into embeddings, we'll store them inside of this vector database. You can also call this, you can call this as your knowledge base, which is a very common term we use. So inside of this knowledge base, if you want to find out anything about certain topic, then you can do a vector search, which is going to use similarity search concept. It's a mathematical concept, but you don't have to worry about it. So it is going to use similarity search to find the n number of most top three, let's say top three. It will search and it will find the top three closest embeddings which are very similar to your query. And this in much detail once we get into the code. So these are all the different web pages from which we are going to do web scraping and store everything in vector database. And along with all these, we can also make use of PDF files. If I visit this link, you can see this is the annual review file. It's gonna take a bit of time to load, I guess. Okay, so this is the PDF file of their annual review for 2024 and document. If I go all the way down, it has about 73 pages. So we have data of 73 pages and I've got these annual reports all the way from 2020 until 2024. So all these 5 reports plus the web pages that we have available on the official website. We are going to take the data, or we just going to scrape all of this text and store them as embeddings. First, let's get into the text scraping part. To do that, I've got this piece of code already constructed. I'll paste it here. Okay, first I'm importing all of my libraries. Here you can see I'm using Beautiful Soup and PyPDF. Both of these along with my request library. I don't think I'm using Beautiful Soup yet, but okay, I'm using request and PDF reader at the moment. I'm creating a folder called as datasets, and this is where I'm going to store all of my data. So I've given all of my links here and the name with which I need to save the extracted text. So whatever text I'm going to extract from the first link will be stored inside of Larsen Turbo overview.txt file. Similarly for the rest of them. And here I'm using all of the PDF URLs for the annual review reports, and I'll be storing them as .pdf files. Okay, so here I've got this function. So this will save all the web pages as text files. So which means this first set, and I've got download and parse PDFs, which will take the PDF URL, which is the second part. It will take those URLs and it is going to download them. And after downloading, I'll take those PDFs, I'll use PDF reader and I'll extract all of the text. I'll store them in .txt file again. And these two functions will be triggered with the help of this one. So I'll take my URL file mapping, which is this big dictionary. I'll pass it to my process function. In the process function, if it is ending with .pdf, I'll send it to this function. If not, I'll send it to this function. Okay, let's run this. I think it should take about a minute or so to extract and parse everything. Okay, it has downloaded one PDF. And in the left hand side, you can see datasets folder, and I've got my PDF created here. As soon as it converts this one into text file, it should jump into the next one. There you go. So we got the text file ready and it has already jumped into the second one. Let's take a look at how this looks like. So this is the text file of the annual report for 2024. And if I scroll here, okay, it was able to read all of this data. But as you can see, this data is quite large. This single text file is about 1800 lines. Okay, so we have extracted all of this data for one file. Let's do the same thing for the rest of the URLs, and then we'll see what we can do on optimizing such huge data into smaller chunks. It was able to read all these different PDFs, and if I explore this one, all of the annual reports are here. And if I go into any one of these web pages, this has very less text actually. Let's take recruitment caution or re-entry for women. You can see that we do have data here, but it is spread out because of the web page layout and all. So we need to do some cleaning up as well before we do any chunking. Okay, but the good thing is we are able to extract all of this data and store them as text files. Now let's go on to the next step, which is chunking. And before chunking, we are going to process the data as well. So I've got this piece of code ready with me here. Let's take a look at what is happening here. So first we have the process text function, and this function will take the text file, file name, and the URL from which this got extracted. So first I'll convert everything into lowercase, and then wherever I've got more than two blank lines, I'll get rid of the extra ones. 2 is the maximum limit. Apart from 2, if I have 3 blank lines, the third one will be removed. Same thing goes for everything that is above 2. Now I'll use recursive character text splitter. I'm getting this one directly from LangChain. So it is a very basic text splitter. So if I've got one sentence, I'll split it into two parts with the help of recursive character text splitter. Let's go back here. Okay, and my chunk size is 1000, which means inside of each chunk I'll have 1000 different tokens. And chunk overlap is, if I've got 1000 here, I'll take the last 100 and I'll make sure that these 100 are present in the second chunk as well. So 100 old ones plus 900 new ones. In that way, there is some overlap between both of these chunks so that I don't miss out on any information. Because let's say the first chunk might capture half of the data and the second one might capture the remaining half. Individual chunks might not make much sense sometimes. They do most of the time, but sometimes there might be cases where your main heading got split into two different chunks. So the heading itself got split, so it's very difficult to identify and understand what each chunk is representing. In those situations, chunk overlap is very useful. That's why I've given 100 as the chunk overlap. Next, I'll take all these chunks and I'm creating a metadata. Metadata is basically a dictionary where I'm storing the file name and the file URL. This is being done so that we have some certain knowledge about from which file did I get this chunk and from which URL did I get that file. Okay, so chunk data is going to be a list of these dictionaries. So it will have the actual chunk along with the metadata, and I'm returning it. And here you can see I'm passing the same URL file mapping. It will take all the URLs, and for every file name, if it is ending with a .txt, it will open that file, it will read that file, and it will send it to the pre-processing. And uh, whatever chunk dictionaries I got, I'll take them, I'll accumulate them inside of this list, and after accumulating it, I'm storing everything in JSON. Let's run this one. It shouldn't take much time. Yeah, 0.2 seconds. Now let's take a look at how the JSON looks like. Ignore it. Okay, so here you can see these are all my chunks. So here is the first one and it's metadata. So which means I got this particular chunk from this text file, and this text file was created using this URL. And you can see the size of the chunk is long enough to store important information. At the same time, we are using some uh, chunk overlap as well. That is why here you can see annual review, leadership, facilities. So if I did not use any chunk overlap, this part will be missing. If I go to the very end of the first chunk, here you can see annual review, leadership, facilities, new, video gallery, so and so. This exact same thing is present in the very beginning of my second chunk. This is chunk overlapping. Okay, let's see how many chunks we have actually created here. If I do Control F, we have 195 chunks. Okay, so each of this chunk is going to be converted into embedding, and that embedding will be stored in my vector database. Now, let's understand what exactly embeddings are and how they look like. To understand it better, you have to watch my previous video where I've explained what is a vector, what is an embedding, and all those things in much more detailed way. But let's take a quick look at it once again. So here I've got two different sentences. This is an example sentence. Each sentence is converted, just very basic. And I'm using sentence transformer library, and I'm using this particular model to convert this string into embedding. Let's run this one. Hopefully it doesn't take much time to create embeddings. We should be able to run and create embeddings on a CPU. We don't need a GPU for this. But if you're doing this on a large scale, here you can see just for this two simple strings, it is taking somewhere about 35 seconds to set up everything, and to create the actual embeddings for the model.encode part, it will take somewhere about 1 minute or so, not more than that. Right now it is taking this 48 seconds and all just to set up everything, because this is the first time I'm importing my sentence transformer. So let's say for this small sentence, if it is taking maybe 7 or 8 seconds, then based on the JSON file that we created, 195 chunks should take somewhere about 4 to 5 minutes to convert each and every single word into an embedding, or each and every chunk into an embedding, and give out this huge list of embeddings. We are not going to store those embeddings anywhere. We are not going to store them in a text file or anything, because you can see each embedding, right now this is a list which has two embeddings, I believe, because we have given two different sentences. But you can see it's a very long array of numbers. These are very small numbers which are capturing the essential meaning, the grammatical meaning, the positional meaning, and all different kinds of meanings. So all those will be captured and stored in this long array of numbers. So it's not readable, of course, so we cannot, there's no meaning of storing them in any text files or anything, so we will embed them directly into our database. So I've got all of my vectors here, embeddings basically, but let's address them as vectors at the moment. So I'll take all these vectors, I'll store them in my vector database. To store them, I'm going to use ChromaDB. ChromaDB is a very popular vector database which is absolutely free, and it does a very basic, it offers a lot of basic functionalities that any vector database should, and which is similarity search. So once I have these embeddings, I can use chromadb.query to query and compare and get the most closest embeddings. So let's convert all the 195 chunks into embeddings and store them in vector database. So here I've got my sentence transformer, I'm importing my ChromaDB, and here you can see I'm creating a persistent client. Let's create it in the same directory actually. So persistent client is going to create an actual file in this repository. Yeah, here you can see there are no folders called knowledge base, so it will create a folder called as knowledge base, and inside of that it will create a SQLite file, I believe, and inside of that it will store all these embeddings. Okay, so you can think of collection as a table inside of a database. So essentially you can create these tables and you can read those tables anytime you want. And because we are creating a persistent client, it will create an actual folder. If not, there is normal client as well. If I get rid of this persistent part and this path, I can use it like this as well, but it will retain only to this particular notebook, to this particular session. If I restart the kernel, it will go away. Okay, so I'm using persistent client, so that will create a folder and it will store all of my embeddings in the SQL file. And inside of that, I'm creating a collection called embeddings collection. Or for this tutorial, I'll just say Gen AI crash course collection. Okay, so this is my collection. Now I'm creating a function here, I'm defining it, which will take the JSON file and it will load all of my chunks. Then I'm separating my sentences from my metadata. So it will take, come on, it will take all these chunk data, it will store them in a list, and then it will take all of the metadata and it will store them in a list. So I've got two of them. They are of the same length, of course. And I'm going to use model.encode to convert everything into embeddings. I'll store them here. Then I'll say collection.add, and I'm just enumerating from my embeddings. So I'll get my IDX, which is the index part. and the actual embedding. So whatever embeddings I've got, I'll put them here. Whatever index I'm getting, I'll put that as my index, and I'll give my metadata here. And this is the actual sentence, actual text value. So in this way, I'm adding all the 195 chunks into my vector database. Created embeddings for length of sentences, which should be 195. Let's run this one. Here I'm passing the same JSON file. Let's see how much time it actually takes. So on the left hand side, you can see it has created this knowledge base folder, and inside of that it is a SQLite file again. So the advantage with this is you can take this SQLite file, you can store it in your cloud, create a backup of it from time to time. You can write SQL queries on it and see how it looks like. If you want to combine it with a different SQLite file, you can do that with basic SQL queries. It's going to act as a normal SQL database. So you can take this and you can convert this into an actual database and store everything online. Oh, it took only 45 seconds. Yeah, so you can take this and store it online. And let's say if you messed up something, or if something unnecessary, something which is distracting or irrelevant got added into the vector database, which is equal to noise, which is a very bad thing, then you can of course take the original one and then replace it here. Okay, so we got all the 195 chunks created and they have been appended into the knowledge base. Let's print the number of items we have in this collection. So I'll say collection.get documents and the length of it, which is 195. So all the 195 got added. Now let's go ahead and query them. So to query it, I'll define one more function here. So here I'm importing numpy. I don't need number for this, honestly. Okay, so this is my fetch top relevant queries function. So here I'll take a query, the collection from which I need to extract, and the top k values. So top k is 10, so which means it will retrieve top 10 closest embeddings. Okay, what I'll do here is query the embeddings model.encode of query. So whatever query I'm passing to this function, whatever question I'm passing, that will be converted into embeddings. Then I'll pass the query embeddings here. Then collection.query will find top 10 closest matches for this embedding. I'll store them in results, and then I'm putting those results in this format: document, metadata, and score. So document is the actual text. Metadata will give me the whatever metadata we have stored for that particular chunk, which should be file name and the URL. And score will tell me how similar is this particular chunk from the query. It is the similarity score, you can see, and it will return me the final dictionary, sorry, the final list. So here I'll ask who are the founders. That is my query. I'll send it here, and whatever 10 results I got, I'm just printing them here. Let's see what we get. Okay, so here we got Mint has conferred the award on Mr. Naik on the recognition of his accomplishments over a long career, blah blah blah. So we got a similarity score of 1.3, 1.49, 1.5, 1.5. Let's put them in a text editor. They are all basically very close to 1.5. Okay, so in this one you can see L&T Group Chairman Mr. A.M. Naik. So we got chairman, which is the question that I asked, who are the founders? Oh, sorry, I asked who are the founders, but maybe this is the closest match that I had in my original data set. Let's ask who is the chairman. Okay, so here I've got all these results. You can see the scores went up 1.7, 1.78, 1.78. This one has 1.8. Okay, so you can see this is how we can retrieve information from the knowledge base. Now, when we are working with ChromaDB, there are many different tricks that you can use to enhance it. Because if you take a look at other vector databases like maybe Llama Parse, it's quite powerful, but essentially all of its functionalities are different logics written for different use cases. So if you have a CSV file, you need to follow a different logic. If you have an image of a person, you have to follow a different logic. If you have image of a graph, you need to follow different logic. What is this logic for? Well, if you have a graph, let's say, the way you read the graph is totally different from how you read an image, how you read a CSV file. So in normal Python code, you can load a CSV file and then you can write your own logic on how you want to convert that table into sentences. You can just take and convert that into a JSON file format, or you can even convert that into a paragraph, or you can send each row into OpenAI or any LLM for that matter, and then ask it to write that as a normal paragraph and then store that paragraph in your vector database. It's completely up to you. So the way we create these embeddings is completely the most building block of how powerful your vector database can be. So today I'm going to teach you very simple tricks that you can use to enhance the quality of your vector database. So the very first rule of creating a good vector database is good data. So there is always a very famous saying, good data in, good data out. So in machine learning, whatever quality that your data is before sending it to the model, that's how good your model outputs are going to be. In a similar way, whatever data that you're converting into embeddings and storing in your vector database, they should be really good. So only when good data goes inside of your vector database, it will be able to query them properly and give you better answers. Okay, so let's take a look at what are these different tricks that I'm going to use today. Uh, I'm not going to use LangChain for this particular tutorial, but you can if you want to. So here I'm importing my OpenAI environment variables OS. I'm loading my environment variables again. I'm taking my token host and model. If you guys haven't watched the previous video, please make sure that you actually go ahead, watch the whole video. Only then you'll be able to understand what exactly am I doing here. Okay, so I'm taking my client, I'm taking my OpenAI, I'm connecting it with the help of my token and my host. Now I've got my messages where I'm saying, you are an AI assistant, tell me about large language models. Let's run this one just to make sure that the connection is working. I've given the max tokens as 256, so it is going to generate a very long output, I guess. Let's see. Okay, we got the output, and yeah, it is somewhat long, but because I've given the max token as 256, it stopped here. It didn't go beyond this part. Okay, that's nice. The connection is working fine. So we are going to create something called as augmented queries. So essentially these augmented queries are different LLM outputs for each chunk. So as I said previously, you can write your own different logic for how you want to deal with different data types and different chunks. And in this case, we are going to take each chunk and we are going to create augmented queries. Let's see how that actually works. I'll paste this piece of code here. Same thing again, I'm importing all of my libraries. I'm giving the random seed as 10 just for simplicity sake of this tutorial. And I'm loading all of my environment variables. My client is here. I don't need this part. I'll just give it as host. I've already given the serving endpoints in the environment variable. Okay, I've got my host here. Now what I'll do is I'll take a random chunk. You can see I'm loading all of my chunks here. I'm taking a random chunk and I'll generate questions. So please generate a set of questions that could be answered using this information. And with the help of fstring, I'm just pasting my random chunk data here. So let's take a look at the JSON again. So what it will do is at random, it is going to choose maybe this one, let's say. So L&T wins Golden Peacock Award for excellence in corporate governance. So I've got this whole text. So based on that, LLM is going to curate and give me a bunch of questions which can be answered from this chunk. So I'll say you are an AI assistant with the ability to generate relevant questions based on the provided text. Your task is to analyze the text, create insightful questions that can be answered using that text. And of course, I want you to return only questions in plain text, multiple lines, no headings, no titles, nothing. No bullet points as well. Okay, so this is my system instruction. I've got my prompt here and I'm creating this message. I'm sending that to OpenAI for chat completion. Whatever responses I get, those are my questions. Whatever random chunk I chose, I'll return the chunk and the generated questions. I'll store both of them in these two variables and let's take a look at how they are looking like. Okay, so here in 4 seconds I got the output. This is my chunk data. This should have my metadata as well. If I scroll to the rightmost, yeah, I've got my metadata, the file name and the URL. Okay, and these are the set of questions that have been created. What is the main goal of climate change mitigation strategy? Okay, this chunk itself is about climate change mitigation strategy. And I've got 10 different questions here. Now what I'll do is I'll take each of these questions, I'll combine the question with chunk data, and that will become my embedding. So I'll take this combined text, I'll convert it to embeddings, I'll store it in vector database. The advantage that I get from this is whenever the user is asking a question similar to climate change mitigation strategy, then this particular chunk will be retrieved very easily. So it will have a very high score. So it will be retrieved and it will be given back to the user, which will be sent to the LLM. So when I'm building a RAG application, I'll be able to retrieve the most accurate or the most closest content from my vector database. So right now we did all of this for one chunk, but essentially if you want to, you can do the same process for each and every single chunk, 195 chunks. It is going to take some time. It will consume a lot of OpenAI tokens as well, but the result is you'll get a very powerful vector database. So let's combine one of these questions with the actual chunk data. So I'm splitting all of my LLM output to get my questions, and I'm taking the first question. This is my augmented chunk. So here I've got my question and the answer will be present within this content. So let's go ahead and create different augmented chunks for the random chunk that we chose. Or basically let's take all the 10 questions and then convert them into augmented chunks. So here I'm taking all these questions and I'm using for loop to create this chunk. I'll store that as the chunk data and I'm appending this new key value called is augmented in my metadata. This is just for safety purpose. Let's say in the future, if you don't want to use any augmented chunks and if you want to use only the original ones, then you can always filter your outputs based on this parameter. So you'll be able to track which of them are augmented, which of them are not augmented. Okay, let's run this one. And here you can see it has created all these different chunks. There should be 10 of them. Let's go ahead and see how many are here. We have 9. Why do we have 9? How many questions did I get? 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 questions. I got 9 different chunks. Okay, now let's go ahead and add all these 9 chunks into our ChromaDB. I'll paste this code here. Same thing again. I'm using sentence transformer model and I'm passing all of my augmented chunks to this function. This will take the sentences, metadata, it will create embeddings out of these sentences, and I want to continue from previous indexing. So whatever I had in the last uh, set of documents, I'll take that length, which should be 195, and it will start the indexing from 195. Okay, so I'm doing enumerate again, embeddings again, the same thing. I'm adding everything into the collection. Now let's run this. It should add 8 to the chroma collection. Sorry, 9. It should add 9. Yeah, 9 got added. So in this way, we can enhance the quality of your embedding, of your chunks. Now, once you add all of these, you can see that for every retrieval, if I go up, for every retrieval, we are getting a similarity score. So we can make use of this similarity score and reduce these 10 chunks into 3 chunks. So whichever chunks have the highest similarity score, I can sort the results based on the similarity score, and I can take the top 3. Because if I'm passing 10 of them, it is going to consume unnecessary tokens. Plus, moreover, whichever documents or whichever chunks have very less score, they are going to act as noise. So if I have a lot of unnecessary details in my prompt, that will affect the LLM output as well. So along with my question, I should send in as much relevant content as possible. I should get rid of irrelevant content. So to do that, we need to make sure that whatever content we are sending has a very close or very high similar score. So along with similarity score, there is also one more parameter that we can use, which is called cross encoder. Uh, but essentially, it is also going to do the same thing. It will take one query and it will take two different string values, and then it will say how similar these two values are on the basis of embeddings, of course. So based on the score that we get, we are going to change the order and we'll take the top 3. This process is called as re-ranking. So let's see how re-ranking can be done. But before that, let's import the cross encoder. Okay, my cross encoder is here. Now I'm pasting this here. Who is the chairman of LNT? I'm getting the top queries, and let's see the queries. Yeah, I've got my similarity score, metadata, and the document. It's exactly has how we have seen in the above code block. This time the scores are slightly high because the query is slightly detailed. I'm asking who is the chairman of LNT. Just because I've added this part, it has given me a higher score. Now I'm going to create cross encoder scores for each of these things. Yeah, here you can see for this document, this was my similarity score and this is my cross encoder score. 6.9, which is very, very high. For this document, I got 0.83, and my encoder score is 0.74, which is very less. My similarity score is 0.89. My cross encoder score is 1, which is okay, I guess. But for this, we got the similarity score 0.95, which is 95%, and we got the encoder score as 5.3. Again, similarity score ranges between 0 to 1, but encoder score ranges between minus infinity to plus infinity. So the higher this value, the more better it is. So what we are going to do is we'll take all these different chunks and then we'll sort them based on the cross encoder score. So I'll paste this one here. Again, it's very basic. I'm taking the query, I'm getting the top queries based on similarity search, and here I'm calculating the cross encoder score. Then I'm using this dot sort method on the dictionary, on the list, and it is going to sort it based on this one, cross encoder score. It's very basic. And then I'm printing my sorted list. So here you can see the top one has 6.99, 6.68, 5.53, 5.14. So even though this has a higher similarity score than the first one, its cross encoder score varies significantly. So that's why we have to understand what exactly is the data we are working with, what sort of queries will be asked. Based on that, we can choose either similarity score or cross encoder score, and based on the data we have, based on queries we get, we can choose whether we want to sort based on cross encoder score or similarity score. Now, once I have the sorted one, I can take the top three, in this case, which will be these three, and then I can take only these documents, which is the chunk text part. I can concatenate them and send them as the context. In the very first course video, you have seen how I've given just one sample 2-line content, which is Rockstar Games has announced GTA 6 trailer in Feb 2024 or something like that, and the game is going to come out in 2025. And then I asked a question, when is GTA 6 coming out? So in that way, in a similar way, I can take all these documents, combine the text, send them as context, and whatever the user has asked for the LLM, that will be the actual question. So these are a couple of methods in which we can improve a vector database. There's also a third method, which is improvising the actual prompt. So when the user asks any question, we can use one more LLM calling. So we can take the question and then we can send a set of instruction to LLM asking it to rewrite the prompt in a much more detailed way. And that will help us to identify the best matching, or at least the closest chunk, very easily. So these are three different ways in which we can optimize or make our vector database much more powerful. If you're learning something new today, hit that like button, comment below with any questions if you have any, and subscribe if you haven't already. Thank you so much for your support.